Let's go ahead and get started. Hello, everyone. My name is Jonathan LeBlanc. I work as a developer evangelist. I've been doing that for about 9 years. Worked as a technologist, author, worked in the identity industries, and with a lot of security technology and social technology. Back in the early OAuth days, I used to work heavily with OAuth 1, OAuth 1OA when they changed that spec. A lot into any different identity security technology that they could throw at us at the time. So I've played in the space for quite a while. It's a fun, constantly changing space. But what I wanted to talk to you all about today is the aspects of, the core rundown of identity and data security. Everything that we're dealing with right now on the web, on mobile, on hardware devices, voice-controlled devices, basically any channel you can possibly think through, and how to secure identity. So a user's login information, a user's account information, how to secure data, so any information, privileged or otherwise, that you want to spit through a channel that might or might not be secure. How do you deal with that? So those are the elements that I'm going to go through. This is kind of a core summation of content from this book that's going to be due out in July. Myself and one of my colleagues are writing it on identity and data security. So this one, unfortunately, for the audience, this one's in Node. My last one was in PHP. So even if you don't get it in the bookstore, please, when you see it in the bookstore, just take the book out and face it in front of all the other books. And if you see a bookstore that has that, you'll know I've already been there. So the core concepts that I go through there is a lot of what I'm going through now on PHP side. So taking a look at how PHP does it, and when you're actually looking at switching the languages and working with identity and data in multiple different languages, you see some languages that do things a lot better, things that that actually work a lot worse. And for the most part, a lot of the work that I've done within the PHP side, it actually works really, really well with some of these technologies. So people have really thought these things through. One of the things that I've learned over the years, one way or another, is that security is hard. Maybe not as hard as Captain Zip Tie over here. This is the best security I've ever seen. I call this Startup Security 101. But realistically, everything that you're going to go through, you have, in an ideal world, you'll not have to have people that have weak passwords. You won't have attackers that are constantly trying to steal their information. You won't have channels that are insecure. You won't have all of these things that are ganging up against you constantly, day in, day out, year after year, forcing you to continuously change and upgrade your security systems. This is a constant hardship that you have to go through, and it's kind of weird. The security folks, the identity folks, they usually don't get any praise from around organizations until something goes wrong. And then it's not praise. Then it's a whole bunch of pissed off people, and usually a lot of cost associated with losing user records, losing credit card information, losing account information. That all comes with a massive price tag. If you look at for instance, the Target data leak several years ago, they lost a massive amount of money in not only what they spent in monitoring people's credit, but also in what they've had to pay for the loss of credit card information and account information. So all of that comes down to, I think, you lose a credit card for a specific user, I think that comes to a cost end-to-end of around $1,000 per credit card lost. So just so you know, that's what you're dealing with in the industry, that there's real physical cost to losing people's data. And one of the biggest problems isn't so much of people attempting to hack these systems, get your entire database of user records, of credit card information. A lot of the times, it's users trying to do it to themselves. And with that, I'd like to bring you the top 25 passwords of 2015. This is always entertaining, and this is great. So usually on the top 10 you see the ones that roll over year after year. Then you actually see some social aspects of what's going on in the particular year. Hey, Star Wars! Chinese New Year's here, ding, right there. So you see certain things come in, certain passwords come in that are indicative of what's going on in the industry. And it's usually films, popular films, but in these data leaks, and this is sourced from, I think it's like 33 or so million leaked passwords, leaked account information from people that has been just released on the web. So they go through this and tally up this list. Now, this accounts for 2.2% of the passwords that are in there. So 2.2% of the passwords are the top 25. But what you also see is when you have massive data leaks from specific companies, and I've seen this in previous years. If you look at 2014, you'll see what I mean. Won't mention any companies. But the company name will pop up on there. So you'll see a particular company name pop up that will, that's where the data leak came from. Then, besides the user's password information of just using weak passwords and us having to deal with that, you also have users that just don't care about how their data is actually processed. Like these lovely people who have left their accounts logged in for some nice people to post on their Facebook accounts. Now, you'll see I blanked out a few things that might not be perfect for the audience, but I'm sure you can get the gist of it. Now, these people are actually quite nice. They posted that there is a problem, but for the most part, some people might not do that. And I'm sure we've all seen this on Facebook accounts from people that we know, from Twitter accounts. They'll say, "My account got hacked." No, you left the damn thing logged in at the Apple Store. that's the biggest problem that you run into, and it ends up leaking data on an individual basis over and over. Users are not that great at securing their own data or protecting their own data. There's very few of them that will use password managers. There will be very few of them who will use extremely unique and good passwords overall. Just passwords that are secure and strong. That's something we don't get. So that's what we have to protect against, and we can do that. We can protect against that. And that leads us into the first topic of protecting a user's identity, and how do you protect it overall. Now, this has become my favorite slide of any of you who are Fallout players. This is my new favorite password slide. But what we're going to talk about a little bit is the attack vectors. The ways that an attacker might attack or try to get your user information. So there's a couple of technical aspects towards this, but there's also some social ones. So you'll have things like using account recovery passwords, or recovery questions. So you have those questions, and the more generic they are, the easier they are to figure out. Typically, the more information that you know about a person, the easier it is to break into their account. I remember just seeing this maybe about a week ago. It was someone had released a list of anti-password security questions. So they were questions like, what was the year in which you gave up all hope? It's the best list I've ever seen. So realistically, it was going on like that. But it proved a good point that these are alternative questions that you can ask. It doesn't have to be as dark as those, but alternative questions that you can ask to make something like that secure. But more information you have, the easier it is to break the account. Now, beyond that, you might have phishing schemes, so email schemes. I'm sure we all had some family member that has clicked on something that they probably shouldn't have within there. That's some legitimate website. They'll be bounced to their Chase account to log in because of some fraudulent activity, and they log in, and all of a sudden their account information is compromised. Those are phishing schemes. Those are social schemes that are utilized against us. But the ones that we're really worried about, or really looking at right here, are the technical ones, because the social ones are a lot harder to actually deal with, because it's maybe providing better account recovery passwords or questions, doing things like providing as much information about the security of the website as possible on the website, which we'll look at in a little bit. But the ones on the technical side that we're looking at are things like brute force attacks. What they'll do is essentially take, let's say, a certain string length, and they'll calculate all potential alphanumeric special characters within there, and then try to push their way through, or try to guess the password that way. Now, obviously, this one works well if you have all the user's information already. So if you are able to collect all the user's data, you have the account information you download, you have all the time in the world to do this. And the longer the passwords, the more exponentially difficult it becomes to try to decrypt that data. So the way that we bypass some of this and utilize some mechanism is something called key stretching. So we take that potentially weak password, we want to say it's monkey, and we stretch it out into a randomized alphanumeric character set, through hashing and stretch out the key. So we make it longer. That's what we're doing. Realistically, that's going to help with brute force attacks. Then doing things like providing CAPTCHAs. CAPTCHAs are a good way of providing on website attacks. So if you have someone that's attacking your site, you should not allow them to have as many password attempts as possible. So what you're going to want to do is shut that down or provide something like CAPTCHA or CAPTCHA in place to prevent that from being done programmatically. Then there's also two-factor auth, so utilizing something like a mobile device, using text messaging to mobile device, using biometric signatures, any alternative factor of authentication will work really well in this case because it's not just relying on that password. Then you have the concepts of dictionary attacks. They get their name because what they're essentially doing is taking a list of predefined words, like the dictionary, and going through those lists as common words. Now, if we go back to this list, you can see how many on this list are actually common words in the dictionary. Football, baseball, welcome, dragon, master. All of it, let's say half of these words are easy to actually pull from this. So dictionary attacks will be very effective in those cases. They tend to also use some different ones that are common, like QWERTY, just because people are lazy and go do and just go across their keyboard that way. So they'll use common words and phrases that way, go through the dictionary attacks. One of the good ways of mitigating this concern is a concept called salting. And what salting is doing is taking your weak password, like banana, and applying a unique string with it. So it's smushing it together. You provide any unique string that you want, and as long as it's randomized, smash it together, you hash them together, and then you get a more secure password. That's how we actually avoid the cases of users using horribly weak passwords. So while we can enforce it on the user side, we can also enforce security on our side by adding salts. Going beyond that, one of the things within dictionary attacks is that, let's say I have a hashed password. So I have a secured password that's stored in my database. And that won't stop really an attacker that's going through it. They can still break those hashes. So dictionary attacks, what they're going to have to do is use the word, apply the cryptographic hash. So basically hash the password, get the hash, and then compare it to the hash that's in the database. That's time consuming. So rainbow tables actually have all the pre-computed hashes at each individual level of the hashing process. So when you hash, you apply an algorithm over and over and over again to get our end hash. So it's storing these hashes at each individual level, and that's what it's using to compare against. So it doesn't have to go through this entire aspect of encrypting the data itself. So speaking of the salting aspects, which is also another preventative measure for this, that gets us into that topic of what salting actually is. How many of you are familiar with the concept? Okay, a number of you. How about peppering? Yeah, that's because peppering is useless. Okay, let me explain this. So the way that salting works is you take that unique piece of data and you apply it to the password, but it doesn't have to. Really, what it's doing is preventing those dictionary and the rainbow table attacks. That's what you prevent. It doesn't have to be stored in a private secure vault. It can be stored right along the side with the user record. The peppering, on the other hand, is a kind of a semi-unique key. It's a private key. So you store that and do the exact same thing with it. Now, the problem with peppering is that it really has no benefit because salting is already there. Salting is also provided by all the hashing mechanisms, hashing functions that are out there, the popular ones for identity, for password security. Peppering is not supported by any of those. So realistically, there's no real benefit towards it, but a lot of people do say it's up and coming. It's not, but it's there in case you want to take a look at it. That's all we will mention about peppering. All right, so let's take a look at how this actually looks. So let's say I'm using some generic hash function. My password is Mechagodzilla because that's an awesome password. So Mechagodzilla, if I hash that, with no salt whatsoever, so no unique piece of data. These are my resulting hashes. They're the same because it's running through the same algorithm. We don't apply anything unique to them. So what this means is when an attacker goes in, they can look at the rainbow tables, compare the hash against that if it's a common word. If it's not a common word and they manage to break the hash, so they go through and try different variations of the string and they actually hash that out and the hash matches, then every other person with the same password in that list is also broken. So they add that hash to their rainbow tables, and then it's easier to break those. Now, if we apply a salt to that, these are utilizing Mechagodzilla again with some randomized salt alphanumeric character string, and we apply those together and run those through the encryption process. The resulting hash that we get is unique every single time. That is why we're trying to do this. We're trying to make this resulting hash completely useless for someone to use. Now, there's a couple of considerations usually when you're working with salts that you should be aware of. Yes?
What are the scenarios if someone could get a hold of that hash?
They can, okay, so what are the scenarios where someone can get a hold of that hash? Your hash is stored in your user records to replace the password. So you don't store a password, a clear text password, you store the hash. If the person, the attacker, potentially can gain access to their account information online, or they can get into the account records, so they hack into the database, download the records, do a DB dump of that, and gain all the records. That's how you get all the account information. And they get access to the hash that way. So when you're storing the salts, they don't need to be private. You can store them right alongside with your user record. It's perfectly fine because all you're doing is messing up the hash. There's difference of opinion here in the industry on this particular thing because technically with the salt, with the proper encryption algorithm, you can run all the words you want through there. You have the hash, you have the salt, so you run that through the encryption algorithm and you can, it's easier to break the hash. But the alternatives to that are using something like peppering, which is not all that supported and really not all that valuable. But there's one really cool hashing algorithm out there that I'll get into in a second that works really well in PHP that actually embeds the salt into the hash, which is really cool. So that mitigates that concern. Then salt reuse, these should always be unique. There's no reason why you shouldn't be using a unique salt because that's going to create a unique end hash every single time, no matter if the passwords are the same. And then there's also difference opinion in the industry on salt length. So I've seen plenty of articles that have said that the resulting hash, let's say the hash is 64 bits or 8 bytes in length, then the salt should be 8 bytes as well. Well, there's one password hashing utility called PBKDF2, stands for Password-Based Key Derivation Function version 2. To its friends, that's how it's known. So they set a default of 64 bits as the standard. Realistically, in the industry right now, 128 bits is standard for what we utilize for generating randomized salts. So 128 bits is ideal for generating salt. All right. So when you're actually using an encryption algorithm to encrypt your passwords, there are 3 main ones in the industry that are regarded as valid. First one, and probably the most popular right now, is called bcrypt. It's specifically designed for password security. A couple of the other ones, the password security was kind of not an afterthought, but it's when some pharmaceutical industry will develop a drug and the side effects are actually what they give people the drug for. So that's exactly what it's like. The side effect was that it was secure for password hashing. It's based on what's called the blowfish cipher, which has been around for a while. And really what you can do with this, which is really nice, is you can scale up the cost of actually running the algorithm. And this is where, this is an important thing within securing passwords, is that you have to make it slow as possible for someone to decrypt the data, but not so slow that the user thinks their site's broken. This will allow you to scale your cost parameter, which essentially applies the algorithm over and over and over again for it to take longer to actually decrypt the data. Then you have PBKDF2, comes from RSA Laboratories, you know, that tiny little security company that you probably have heard of somewhere. So it has a good research background. So this is actually a pretty simple one in much the same way as bcrypt applies that same algorithm over and over again. It performs and the HMAC, which is a hash plus key, and it provides that over iteration, over iteration, over iteration. So basically applying an algorithm over and over again to get an end result. That's what it's trying to do. Now, the one that's a little bit different, script, is really, really cool. So the main issues here and here is that even though you can scale up the security on how long it takes, let's say, an individual computer to actually break down a hash, these are really great to run in parallel. So you can run these mechanisms in parallel. So the more computers you add, the quicker it is to break the data. Script, on the other hand, is really great, or script, whichever way you want to say it, is really great because it mitigates large-scale hardware attacks because it's very memory intensive as opposed to utilizing the CPU. So you have to have a lot of physical memory present in order to blow out the hash on each side, on each time, every time you want to decrypt the data. So you have to add a frig load of hardware in order to get something really valuable by using this one. And depending on the language that you're using, there are preferences within the language creators, the people who maintain the language. So in PHP, for instance, bcrypt is one of the main ones that is pushed in a lot of the cryptographical hash functions. Within Node, the standard crypto library utilizes PBKDF2. And typically, you're going to see most of the uses in bcrypt or PBKDF2. So those are your two most popular ones. So let's see how these actually work. So if we go through a practical code example on implementing these in PHP. So let's say I have a user that has created a brand new account. They create their account information, their username and password. So they pass it through to our script that we can run to hash the password. So we capture our user's password. Then the bcrypt hashing function over here utilizes an options list. So there's a couple of options that you can specify. The first one is the cost, which is essentially how long it takes to decrypt, encrypt, etc. Right now for bcrypt only, a cost parameter of 12 is appropriate, and depending on the hardware that you actually have, it's going to take less or more time. It really depends on the hardware. But that's the standard in the industry for the cost parameter to utilize. Anything beyond there, it becomes exponentially longer to actually decrypt, encrypt the data. So you'll be running into a couple of seconds to go through all this when you really don't want that, because then people, adding 3 seconds of load time towards your website is not a good thing. So cost parameter of 12. Then we're actually going to run password hash. Now password hash is going to run bcrypt for us. So we specify in the parameters the password, the plain text password that is provided to us. Password bcrypt here. I believe the other option is password default, if I can remember correctly. Yeah. So password bcrypt here, we're going to run on bcrypt. One thing to note here is this little option here. The salt option can be applied here, so you can specify your own salt. But it's deprecated as of PHP 7+. So what happens here is when you run that, a unique salt will be generated for you, so you don't have to worry about it. Now, as you see, we're not dealing with the salt at all here, because the salt is generated and pushed into the hash itself. So all we need to do is store the hash wherever we would put the password. So we throw out the password, store the hash. Now the way that these hashing algorithms work is that they're one-way. So they encrypt, they do not decrypt. So when you actually have to decrypt this data, you compare resulting hashes, you don't decrypt a existing hash. Like this. So user comes to log into a system, they provide their username and password. Capture that. Then we fetch some DB record from our database. So we're fetching the user record, username, password, username, hash, and whatever else might be in there. Then we run this function, password verify, passing through my password. So my plain text password that has been supplied with a login attempt against my hash that I have stored in my user record. If those match, then the password is verified and you can log the user in. Behind the scenes, what's going on is this plain text password is being run through the same encryption algorithms using the same salt that's supplied in here, and actually generating a hash. Then it's doing a comparison of the hash. It's just doing it really nicely for us. An important thing to note here within comparison of hashes is that do not do this yourself. And actually, this is a general rule within security in general. Do not do it yourself. Utilize systems, functions, methods that are already available by companies like RSA Laboratories, researchers in the security industry, because it's very difficult and it's very easy to screw up one little thing, which completely destroys your entire security system. Now, this one, for instance, in comparing hashes, if you just do a standard hash, or if you just compare strings yourself, you open yourself up to what's called a timing attack. So measuring how long it takes to encrypt or decrypt data can be utilized as an attack vector to be able to figure out what the hash is, the root password of the hash. It's, so you want to utilize verification systems like this instead of doing it yourself. All right, so that's essentially what you're doing on the bcrypt side. Now, looking at PBKDF2 is slightly different because we have nothing to deal with the salt here. So we're dealing with the salt ourselves. We're generating it ourselves, and we're storing it ourselves. So again, we capture the user's password. So they created a new account. We capture that password that we want to encrypt. We specify the number of iterations, and you notice this is different than the iterations is the same as the cost parameter within bcrypt, but different algorithm, different cost. Standard in the industry default is 1,000 for PBKDF2, so that's the times it's applied. So we set up our iterations, we create our general salt. We can use this function here, encrypt create IV. IV stands for an initialization vector. I'll get into that in a minute because it makes sense within data encryption. It doesn't really make sense here. So I'm going to put a pin in that one. But what I'm doing is creating a generic string, an alphanumeric character string of 16 bytes. That's what I'm doing. So at the end, our salt will just be that string. And this encrypt dev urandom is where the passwords are, or the strings are actually sourced from. You can use dev random is another one, and there's a couple of others beyond that. Then we actually hash this thing out so that the hashing function here is hash PBKDF2, utilizing on top of that the SHA-256 algorithm, which is used for another data encryption. And then passing through the password, so the plain text password, the salt that we specified, the number of iterations, and 20 is the resulting length of the hash. So then we take the hash and we take the salt, and then we store it in our database record. So again, we have a user record. We pass the hash in. The hash is our password. The salt's stored with. All right, then this gets a little bit bigger when we start actually going through and trying to decrypt the data. And it actually shows the steps that we have to go through in order to decrypt a little bit better than bcrypt does. So again, we pull out our username and password from the login attempt. So the user logs in with a username and password, and we want to verify that. We set up the same number of iterations that we're going to do because we need to encrypt this new password. Fetch the user's record from the database. So now we have so basically now we have the hash and the salt. That's what we really care about here. Then this is where things get a little bit different before the comparison. Now we're going to do this manually. So we're going to we're going to take that new password from the login attempt and run it through our same hashing algorithm that we did before, PBKDF2, utilizing the same information, so same algorithm, the new password, which should or might not be the same salt that was used to encrypt the original password for the account, same iterations and same length. So if everything is the same, including the password, that's the only variable here that might be different. The resulting hash should be the same from the login attempt to my account hash. Then we run hash equals, and that's just going to measure two hashes and do it in a way that prevents these timing attacks that I mentioned before. So it's just comparing these two hash strings. If they match, then we log the user in. If it doesn't, then we spit them back. All right, so that's kind of crash course on password security, on everything that you're going to be dealing with actually protecting your user's password. There's a lot more to it, but there's only a certain amount of time in a day. All right, so next up, let's go into protecting users' data. And I love this picture. I want to see this somewhere. Okay, so what you're going to notice is, as we're going through some of these practical examples, you're going to actually see some similarities towards the password hashing as you will in data encryption. How many of you here have worked with OAuth 1, 2, 1OA? Okay, you'll notice a lot of similarities. How many of you have worked with website certificates? Okay, you'll notice a lot of similarities. Basically, we're using a lot of keys here. Whether 1 key, 2 key, 4 key, there's a whole bunch of different ways that we can do this. I'll show you a couple of examples. Now, our ideal scenario, is to basically use SSL TLS. Transport layer security is basically the newer way of SSL. So it's the new algorithm that's utilized, but typically when people are talking about SSL, they mean this. So they lump them all in together. But that's essentially what we want to set up. And I'll show you how to actually set up a certificate, a self-signed certificate in just a second, and what that actually means. It helps quite tremendously for actually testing and for understanding the key process. Now, typically when you're doing this, what you're essentially doing is encrypting an entire channel from a browser to a server. You're going to encrypt the data through. It's an ideal situation. It works really well for the last, quite a while in utilizing this type of system, because we didn't have a lot of hardware that was out there that was web connected. We didn't have a lot of connected devices that might not provide secure channels. We didn't have voice command systems that provided that data through. So there's a lot of systems now that just use very insecure channels where this isn't something that we can use. But in an ideal scenario, that's what we're dealing with. Now, when you're actually going through to a certificate authority, so you go to GoDaddy or DigiCert or a whole bunch of other ones out there, and you get a certificate or buy a certificate for to make your website nice, little HTTPS secured, a little secured lock in the corner. There are 3 different types of process that they'll actually push you through, and it'll actually change the way that it's actually viewed on your site. So the first one is called domain validation. Essentially, what they're going to do is validate that you have admin access to the website only. So when you actually set up a certificate request, you have to provide a lot of company information and a lot of user information. So basically, it's maybe 10 different pieces of information that it'll ask you. All that's thrown out, and all they want to do is make sure that you have access to the actual website, have admin access. So that's all they're going to verify. Once you install that certificate, you get the green lock. Da, 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 da. First step. Then, one of probably the more popular ones, organizational validation. What they're going to do is validate not only that you have admin access to the domain, but they're also going to validate that some basic information. So basic details like your address, the name of the company, things like that. Now, what you get from that is that lock up in the URL bar, plus information on the company and the individual within the certificate. So if I click on that lock and I view information about the certificate, it's displayed. The last one is an extended validation. Now, it does all the previous ones, so domain validation, it's actually going to validate some basic information about you and your company, but then it's going to validate the actual legal entity of your company. So it takes a little bit longer, but when you do that, you actually get full-blown nice security system with your actual company name in there. So that's what you're getting from that. Search is the same, security is the same. It's just how it's displayed to the user. So any of the validation systems are actually pretty useful, depending on the one that you want to go through. Now, let me show you how to do this yourself. So there's a way of self-signing a certificate so that you don't have to pay the $150+ for a certificate to buy a certificate from a certificate authority. Caveat here, Never, ever, ever do this in production. This is testing only. So this is for actually testing the secure system. You can actually set up all of this beforehand before you actually buy the certificate. And so if you want to test out some systems, you can utilize it this way. Now the reason you never ever want to push it to production is that you guys have all seen these things, right? You hit a site and then this pops up. That's because it's a self-signed certificate. The browser doesn't trust it. No one trusts it, so it's going to pop this up. And this tiny little link down here will allow people to go to your website. That's why you never want to use it in production. Only for testing. Okay, so first off, how we're actually going to do this is we have to create a couple of, basically a couple of keys. So this one thing breaks down into a 4-step process. So if you're breaking this down into individual steps, the first thing that you're going to do is create a private key. Your private key is, just that. It's a private key. It's a private alphanumeric character string that is utilized for part of the validation process. Second step that you'll be going through is creating what's called a certificate signing request. It stores itself as a .csr file. Now, the certificate signing request is where they're going to ask you your company information and information about yourself, your email address, and all of those details. That's what gets dumped into that certificate. That is typically what ends up being supplied to a certificate authority. So that's what they ask for, like the GoDaddies, the DigiCerts, etc. That's the information that they want in order to actually build your certificate, or give you your certificate. Third optional step is to actually remove all of the password security and the encryption off of your private key. This is only done for testing. And it's actually quite valuable for testing because then you don't have to deal with password security or any of the encryption details if it's only for testing. The last one is actually creating your self-signed certificate file, the .crt. So this .crt file will be your actual certificate. If you open them up, they both look essentially like keys, like alphanumeric character strings. That's all they look like. But this nice little line does all 4 of those steps for us. So we call this OpenSSL request on our terminal window. -X509 specifies that you should create a self-signed certificate as opposed to a certificate request because we're bypassing that step. Nodes is specifying that you actually want to remove password security or the encryption from your private key, so it does that automatically. Specify the number of days that the certificate is valid for, 365. Generate a new key, a new RSA key of a particular bit length, and then we generate our server.key, that's our private key, and our self-signed certificate file, which is server.crt. That is going to dump it in the same directory that I run this in. I can just push these anywhere. Okay, next up, what we have to do is set up, let's say I have my Apache installed. Just to do a couple of little things in order to get it running. So in my hbd.conf file, all I have to do is search for these 2 lines here, so mod ssl.so, as well as my hbd-ssl.conf. So those files will enable SSL to work on my desktop. So uncomment those, get rid of the hashes. Then load up this file here, this hbd-ssl.conf. And that's where we're actually going to specify where our certificate file is. So you search for this line, this SSL certificate file, and it'll have some default in it. For me, specified as that default. So the default directory, we can either dump our certificate file in and our private key wherever we want. So I'm basically dumping that information in and copying everything over. Or we can specify some other private directory ourselves, wherever we want to store it, but we just have to reference it within that SSL certificate file. Then, I'm sure now you know the next step, add a virtual host entry. Everything's pretty well standard within entering of a new virtual host entry, except for these 3 lines here. This is specifying that we should run this with basically the SSL engine. We're specifying the certificate file as well as our private key file. I'll also be giving you a link at the end towards the slides in case you want to download any of this information. All right, so that's pretty much everything you have to do. Once you load up your website, in my case it's SSL test. When I run that, I am the proud new owner of this nice warning page. So Then I can go ahead and start working with my secure server, start sending requests through to it, start working with my HBS in secure domain. All right, now that is ideal scenario. What happens if we're not in an ideal scenario? What happens if we're working with some piece of hardware that doesn't provide this functionality? How many of you have worked with beacons before, like Eskimos or Blue Cats? Okay, a few. So essentially, a beacon is a tiny little Bluetooth low energy connected device. It's a little piece of hardware. It sits somewhere. Now, Eskimo beacons, the way they work is they broadcast out a location saying who's around me. And they can connect through mobile applications on your phone and load up an application for the store. Other beacons out there, the way that they work is that the beacon works as a bridge. So your phone connects to the beacon to a particular store, so it's location aware. Then the beacon itself connects to an endpoint. So let's say that's some web endpoint to be able to check out. So you pick out your items in the aisle, you click on the application in your phone, you pay for them right on your phone, so you're basically doing in-aisle purchasing. Those are some things that you can do with beacons. The beacons are completely insecure as far as a channel. So you have to secure the data as it's being sent through. The beacons cannot decrypt, encrypt, understand any of the information beyond just connect to the phone. That's all it can understand, and who's around you. Basic information. So it works as a bridge. Now all this information that's being sent through can be sniffed by attackers and can be pulled from by attackers. Now without the proper keys to be able to decrypt the data, it's useless to them. So that's exactly the types of systems that we'll be using. Now there's two particular ones that I want to go through. One's called synchronous cryptography, essentially one shared key, and the other one's symmetric and asymmetric. So they use a couple of different names for this. The asymmetric key cryptography or public-private key cryptography utilizes either 2 or 4 keys, which I'll show you in a little bit. Okay. This one, the way that it works is you have your sender and your receiver. So let's say browser and a server. They're going to encrypt the data with a single shared secret. So when I created those keys, that private key, let's say when I set up my SSL cert, it'd be the same thing, creating a private key. So encrypt the data with that private key, it gives you ciphertext. Ciphertext is some scrambled piece of text. It's encrypted text, encrypted data. That is sent through to my receiver, so my server, and the same private key, same shared key between the sender and the receiver is used to decrypt the data. So that's how it generally works. It's utilized quite heavily, but one of the biggest problems is that if this thing is compromised, it basically opens up the entire system towards potential attack. So it works really well when you have a single user environment, one person on one browser connecting to one endpoint, one sender, one receiver. It works really well in those implementations as opposed to a multi-user environment. Typically, let's say the way that you can use this is when you create an application on a system. So some API provides you access to an application. Typically, nowadays you'll get 2 keys, a public and a private key that you can utilize. And I'll get into how to utilize that in a minute. But technically, you can provide one key, one shared key, and that shared key can be utilized on your site. So you copy that over to your application directory in some secure location. It's the same one that they can use for decrypting the data. Okay, so one of the things that we have to understand before we jump into this is actually when you're actually running these encryption algorithms, not only the encryption algorithm, but there's these things called modes of operation. Modes of operation affect how the ciphertext is actually created. Typically, within an encryption algorithm, it employs some block cipher. So a block cipher, what it's going to do is take your message, your raw message, split it up into individual blocks, and encrypt each block. Now, the modes of operations affect how that's actually done. So sometimes you can run all those blocks in parallel, so you can encrypt all of them in parallel. It speeds up the process. Sometimes you have to rely on the previous block to be encrypted before you can encrypt the next block. It depends on the mode of operation, and they do different things. So modes of operation are actually split up into 3 main sections within the NIST standards. So NIST.org, I think it is, if you go there, they set up technology and computer science standards for the industry. So they specified three main groupings for these modes of operation. Encryption, which is basically data encryption. So you encrypt the data, so if the information is stolen somewhere along this channel, if they don't have the keys to the private keys, they can't decrypt the data. They can't encrypt their own data and send it to the end user with that, without the key either. So those include five modes. They're called ECB, CBC, OFB, CFB, CTR. Don't ask me what they all mean when you actually bring them out, because I cannot remember the names except for counter. So the other ones, I forget their names. But that's essentially what they're doing. They're encrypting. Now, some of them are slightly different. So I think it's ECB, for instance. It splits its blocks, and then you can run everything in parallel. So you basically can encrypt each block in parallel. CBC, you have to wait for. You have to basically wait for the previous block to be encrypted before encrypting the next block. So it gets a little bit complicated depending on the usage. Some of them slow you down, some of them don't. Some of them are better for parallel processing. Some of them are better for random things. So take a look at the modes of operation and what they do, and then you'll figure out which one's best for you. I'll show you a couple of examples. Authentication mode, it only has one mode of operation, CMAC. To be honest, it's really, really useless for the vast majority of the implementations that I've seen out there. All it's really doing is verifying that that it's actually the sender that I'm intending the sender to be that's sending the message. So I'm verifying the sender of the message. That's all I'm doing. The data that's sent through utilizing this system, it shouldn't be privileged in any sort of way. It shouldn't be something that needs to be secured in any sort of way. All you really need in this, and all you really want, is to verify the sender. That's all you're doing. Now, the one that's really valuable that a lot of people tend to use is called authenticating encryption. It includes both these previous ones. So you verify the sender and you encrypt the data. There are five main modes here: CCM, GCM, and then three for key swapping here, key wrapping here. KW, KWP, and TKW. They're really stuck together. The most popular ones in each of these categories, so under encryption for industry standards that are utilized mostly, counter, CTR, and CPC is typically used. Authentication, CMAC, just because it's there. It's the only one. And under authenticated encryption, GCM is the most popular in the industry that's used. But again, it depends on your application and what you're doing with it. All right, so with that said, let me show you some practical examples of how this actually works. So if I want to encrypt data with a single key, this is how I can do it. What I'm doing here is creating two random keys. So in the same way that I was creating private keys before, or I was creating salts before, it does the exact same thing. So realistically, what I'm creating here is a private key, so that shared private key, and that would be saved with my sender and receiver. So this can be run when the application is actually created. There's this thing called an IV, or an initialization vector. I said I would pin it until I got to this section to talk about data encryption. An initialization vector, the way that it works is talk about the block ciphers and how they work by splitting up each parts of a message. So a couple of characters in one block, a couple of characters in another, and then they try to encrypt each block. Well, some of them, like CBC encryption that we're looking at right now, CBC mode, what it does is it relies on the previous block to be encrypted before it encrypts the next one. So block 2 relies on block 1, block 3 on block 2, but block 1 has nothing to start with. So in order to start it off with some piece of data and actually make the cipher work correctly, we have to provide an initialization vector, which is a randomized piece of data. So again, private key and initialization vector. Then we call OpenSSL encrypt, passing through our plain text message, so the message that we want to encrypt, the mode. The mode here is using AES, AES encryption. So this is industry standard. It's I believe its predecessor was DES, but it's usually the one that's utilized in the industry. And then 256 mode CPC mode encryption. So that's what it's utilizing as our mode of operation and our algorithm. So that's typically standard depending on your mode of operation that you want to run. Then you provide your private key. The 0 there is that we're specifying no options. here, because all we're doing is encrypting the data and then providing that initialization vector so that the block cipher can be run correctly. All right, so now what happens is when I send information to my server, I'm sending through my initialization vector, or I have to provide my initialization vector, and then the ciphertext, which is that encrypted text, that encrypted data. So that is sent over to the server, transferred over. What should be already known by the server is that key. So when I called when I actually created this key, this should be done on application creation. So when I create an application with a service, it creates the key that I can utilize. But for the sake of this example, we're just creating it here. So that's known by them. We use the same mode, the same encryption mode as we did before. And then we just encrypt the data with OpenSSL decrypt, providing in the encrypted cipher, so the ciphertext, the encrypted data. Same mode, same key, no options, and then the same initialization vector. So these, unlike password security, are two-way. So you can encrypt and you can decrypt. That's how you would typically do it with this system. Now, if you want to see all the modes that are available to you, this is a really handy little function. OpenSSL get cipher methods. It's going to dump out an entire list for you. I think I had there. So this is the output that you would typically see. Let me drag this over. Yeah. Well, this is the output that you would typically see. You would see the algorithm and then the mode over here. So you can utilize whichever one works for you. Cool. Okay. Now the other one, and probably one that you're familiar with when using different algorithms like the OAuth or multi-key systems, is called asynchronous cryptography. It's also known as public-private key cryptography. It uses two keys. So the way that this works is a little bit different. There's two different modes you can run in. So at a basic level, if you just want to encrypt and decrypt and you don't want to verify where the sender that it's coming from a specific sender, you can use one key set, so a public and a private key, much like a username and a password. A public is the username, private is the password. Okay, so the receiver or the sender will encrypt with that public key, creating the ciphertext, and then the receiver will decrypt with a private key. So it's one key set that's shared between them. They each involve one piece. Now, if you want to verify, you do the exact same thing. You create a duplicate ciphertext, but instead you utilize the sender's private key as opposed to the public key. And then when you decrypt on the receiver side with the sender's public key. So these public keys, typically you can get them from a public key store. So you can set up a public key store where people can look up the information and pull the information if they're valid applications. You can do it in a number of different ways, but these don't have to be as secure. It's the private keys that have to be stored specifically in a secure location either on the sender or the receiver. But you can see that it's opposite keys that are being used. Receiver public key, sender private key that's being used right there for the encryption process. And then the decryption uses the opposite keys. All right, so these are really good for multi-user environments. So if you have a many-to-one relationship, a lot of people that are sending in messages towards one server, the end server, as opposed to the other methodology which works in a one-to-one relationship. Now, the way that this is going to work, and to set up our keys, we just need to create our private and our public. So if we use OpenSSL gen RSA, so it's going to generate an RSA key for us, creating our private.key, specific bit length of 2048. So that's going to generate our private key. Again, alphanumeric character string stuck within there. It's just a standard key. Then utilizing that private key, we generate our public key stored in a .pem file. It doesn't have to be a .pem file. When I was first studying these long time ago, I always wondered why people would put them in a .pem. Some people would put them in a .key file, and why some worked and why they all worked together. Well, the reason why they worked is when they were setting up standards for key storage, so where to store your keys in any particular container. So a container being the file. There were a whole bunch of competing formats out there. .pem, .key, whatever, and none of them took hold. So you can basically use any of them. Doesn't really matter. All right, so you generate your keys here. Now we have a private key and a public key. We're going through just the encryption side just to show you how it'll actually work. So what we're going to do first off is, as the sender is sending some piece of information to our end receiver. We capture that public key, get its file contents. So we pull that key down, set up basically the JSON string that I want to utilize in order to send that data through. Then I use a process called seal. Now this is where actually PHP is better than other languages at doing this, because it works really well for this multi-user environment. It uses this concept called an envelope. So when you're sending through a bunch of requests all together, you can actually send in multiple public keys. So you can have multiple public keys that are encrypting data all at the exact same time. So when you have that set up, it works really well for the system to basically send a whole bunch of messages all at the same time. So we use OpenSSL seal, passing through the data that we want to encrypt. These two variables will basically what will be dumped to those is the encrypted data, so the ciphertext that is generated from that, and then our encrypted public keys. So the public keys will be taken and encrypted to be utilized later for decryption. And then we supply an array of public keys, so however many public keys we have that are being sent for multiple users. Then we basically capture these data, get this data ready for or encoded for sending. It'll be our sealed data and our envelope, and we transfer those two pieces of data to the recipient, so our server. Now on the server side, we are going to obtain that data that came from the sender. Now this is a completely insecure channel that's coming through. We've just encrypted the data. It can be over HTTP. It doesn't have to be encrypted. We extract our private key, so that's the matching key set. We decode that data that was sent through to us, and then we call OpenSSL open, passing through our sealed data. This variable will be where the data is dumped to. So plain text will be the unencrypted data. Passing through our envelope of public keys, and then passing through our private key. That will decrypt the message, and then we can start utilizing it. Now, if I wanted to do the verification step, I basically do the exact same thing. So I'm basically seal the data, but I use, instead of the public key, or the receiver's public key, I use my private key, my sender's private key. So you just swap the keys. You run it twice. You send 4 pieces of data through. And as you can tell, by sending 4 pieces of data through, this is a slow system. It's not really good for encrypting a large piece of data. So it works really well with hardware implementations where you're sending simple JSON commands through. It works really well within systems like beacons. So that's pretty much data security in a nutshell. A few of the methodologies that you can utilize to encrypt data through both secure and insecure channels. Essentially, you're using keys. That's an industry standard to utilize either a single shared key or multiple keys. But when you really look at it, there are some fundamental sameness amongst everything that we're doing. Encrypting passwords, encrypting data. It's all the same. We're trying to protect the users in whatever channel they're in. We need to protect the users from themselves, and then we need to protect them from attackers. So everything that we're doing is either strengthening what the user has provided us or encrypting it to a degree where it's useless for an attacker to get to. But realistically, in things like password security, what you're doing is just slowing down an attacker. They get your entire series of user records. They download that. They have all the time in the world to decrypt the data. But you want it to take as long as possible for them to do that so that you, as an administrator or as the identity provider or what have you, has enough time to basically log people out, revoke their passwords, etc., whatever you want to do. Slack did this a year or so ago when their systems were breached. They used, I believe, bcrypt for their encryption mechanism. So the passwords are fairly secure, but they provided admins of their groups access to auto-revoke a user's password so that they had to enter a new one, or auto-log them out to protect their systems. And they were able to do that, and really nothing was lost. So that's what you're really trying to do here, is just slow down the attacker. So again, thank you very much, everyone, for your time. I appreciate you all listening to this. If you want the slides, they're right up here. This is the link to the slides. Contains all the information that I provided, the code, etc. I'm going to be pushing out the code samples today, sometime. and you can just pull those down as well. They're a little bit more comprehensive code samples for running through each of the things that we talked about today.